Okay, welcome back, dear friends. I would be discussing the Carnot engine and take up the poll questions related to the same. I'm sure you have listened to the video on Carnot engine, and we would be revising this concept obviously. But as you know, that I start the session with the poll question, right? So I'm launching the first poll question to get your responses, and then we would begin the discussion. Okay. I'm about to close the poll. It's a very simple question, and this is to ensure that you are taking the coursework very seriously. However, looking at the responses, it appears to me that you haven't, I mean to say, 40% of the students haven't listened to the video. Okay, so this is a bit serious. So let me close this poll. About 97, 96 of the students have joined. Okay, and they would be considered present physically. Let me share you the result which most of you have answered. Okay, the question was uh, whether the Carnot engine could be constructed. Okay, practically speaking, right? And this was a very straightforward question, according to me. Uh, before I answer this, let me stop the polling. Okay, so I've closed the poll and I'm sharing the result. Okay, hopefully you are able to see the answers of the poll. Yeah, ma'am. Yes, yes or no? Yes. Okay. Okay. Thank you, Vedant. Uh, see, what was asked? What was asked was whether Carnot engine is a practical engine, right? Because this is a very straightforward question. Carnot engine is an idea. Okay, it is not a practical engine. It is an idea, and it cannot be constructed. This has been emphasized in the videos which were circulated to you. Okay, yesterday. Mm, please note that why are we talking about Carnot engine? Okay. Carnot engine is an ideal heat engine. Okay, I'm going a bit slow so that you appreciate this better. See, I'm stressing this again and again that Carnot engine is an ideal heat engine. When you are saying that it is an ideal heat engine, automatically it means that this engine cannot exist. Okay, this engine cannot exist. So you can you can do a thought exercise, okay, in your mind that how the Carnot engine could be work, right? And how do we visualize the processes which are happening in the Carnot engine? So this we can think of as an idea, right? But if you want to physically construct a Carnot engine, and I'm not talking about simply mechanical construction, constructing a heat engine, okay, to behave as a Carnot engine, such that they execute all the four processes, all the four processes. So we were talking about the four processes of Carnot engine, right? And those four processes, they are all ideal processes, and those ideal processes cannot be actually carried out in any engine. Okay, so Carnot engine cannot uh, cannot construct the Carnot engine cannot be constructed. Okay, let me hide the yes Sonone. Yeah, you are seeing the result and I'm actually discussing the result. So I am not actually talking about I have not drawn the Carnot engine. Carnot engine, as the result says, 36% are saying that it can be constructed. They are totally wrong. Okay, the students, 64% of the students are right. Okay, and the correct answer to this question is Carnot engine, a practical Carnot engine cannot be constructed. Okay, we can think of a Carnot engine. We can, in our thought process, okay, we can do a thinking exercise and we can visualize how a Carnot engine could be. But practically speaking, no Carnot engine, okay, no Carnot engine is practically possible to be constructed such that they execute the four processes which we talk about in the Carnot cycle. Please note that the answer is false to this question. Okay. Before I take up the discussion of what is a Carnot engine, I want to be very sure that you have understood the central concept of Carnot engine. Okay. So for that, I would be asking you the second question. Okay, a second question, and which is very important question, and hopefully you would answer it correctly. This is a bit tricky question, and this would be answered only if you have got the concept very right. Okay, so let us see how many of you are really listening to the videos and getting the concepts So what is asked is Carnot engine. The question is, a Carnot engine is an ideal imaginary engine. It's an ideal imaginary engine whose efficiency is 100%. Okay, whose efficiency is 100%. That is a question, very straightforward question. Carnot engine is an ideal imaginary engine whose efficiency is 100%. Surprisingly, majority of the students are making mistake in answering this. And what could be the reason? Okay, Suranjay. Okay, Suranjay. What is your first name, Suranjay? Raju. Okay. So Raju is saying that yes, it cannot be 100%, right? So let us see now how many of you agree with Raju. Okay. Who else is saying that? Okay, somebody else, Archie or what? I'm sorry, I'm not able to read the complete name. Roll number 7, division B, is saying that the answer is false. Okay, let us see. Let us wait and let us discuss this. This is very critical and important concept. You need to understand this very clearly, and that is why I'm spending so much time on this. Very preliminary kind of discussion I would be having with you. So let me close the poll before I start the discussion. Okay, wait for a few seconds before I have 90% of the students have voted, and most of you have voted incorrectly. Okay, most of you have voted incorrectly. That is surprising. Okay, the question is, listen to the question. Carnot engine is an ideal imaginary engine. Carnot engine is an ideal imaginary engine whose efficiency is 100%. Okay, we close the poll and let me show you the result. The poll is closed and I hope you are able to see the result. Yes. So 62% of the students are saying, okay, 62% of the students are saying that the efficiency of the Carnot engine is 100%. 38% of the students are saying that efficiency of the Carnot engine cannot be 100%. So in spite of the fact that 38% of the students are in minority, okay, so we won't be using the majority rule here to decide on the answer. The answer is false, and this has to be very clearly understood. Okay, please note that we are talking about a Carnot engine, which is an ideal machine. However, even a Carnot engine, cannot have an efficiency of 100%. Okay, and why it cannot have an efficiency 100%? Okay, I will go to the next question, and you will understand that. Okay, please listen. The answer is what? Answer is false, and 38% of the students have answered it correctly. 62% of them have wrongly answered. Okay, they haven't understood the concept. I will be repeating this concept again But before that, I will just ask one more question before I take up the discussion on Carnot Engine. Okay. So I'll be hiding the result and I would be asking another question. Okay. And that would probably help you appreciate what I'm trying to say. That would probably help you appreciate what I'm trying to say. A question is, Carnot engine is an imaginary engine which violates the Kelvin-Planck statement. Okay, it's an imaginary engine. It is not the real engine. It's an imaginary engine which violates the Kelvin-Planck statement. So again, there is a lot of confusion looking at the results, which looking at the answers which you students are giving. Okay, I'm sure you are confused a lot. Okay, you are not very clear. Obviously, 50% of the class is very clear conceptually, but I'm not talking about those 50%. I'm talking about the remaining 50% who are not getting this concept, and I need to make sure that the entire class, okay, if not entire class, at least 90% of the students, they understand this concept very clearly. Okay, so I'm going to repeat this concept and I'm going to emphasize on this point, but let me first finish up this poll. Okay, so please vote fast. Only 68% of the students have voted so far. So you need to hurry up. It's simply a true false kind of question and it does not require any calculations. Okay, so let me close this poll and let me discuss this concept a bit. Okay. Okay, so there are some students, very clever students in the class like Zai, Archit, Raju. They are understanding this concept, Omkar. Okay, but there are many who now, for example, Ritesh Patil is saying that its efficiency is about 70% or so. Okay, Ganesh Shikare is clear on the concept, but let me now first um, discuss this a bit so that I'll close the poll, right? And see, looking at the result, let me share the result. Look at the result. The result says that 46% of the students are wrong. Okay, 46% of the students are wrong. So the correct answer is false. Correct answer is false. Now, what was the question? The question was whether a Carnot engine violates the second law of thermodynamics. Obviously, we had said that no engine, okay, no engine can violate the second law of thermodynamics. Okay, so the Carnot engine also cannot violate the second law of thermodynamics. And why is that so? Let me hide this first. Whether the whiteboard is seen to you? Whether the whiteboard, no, not seen. Okay, okay. I will share the. Let me close this first. Okay. Now whether the whiteboard is seen? Whiteboard is seen or no? Yes. Okay. Thank you, Singh. Mm, okay. No, no, it's not seen. Okay. Now let me. Now it's seen. Not seen. Okay. All right. Just a minute. Let me close this. Now it's seen. I hope it is seen now. Okay. It's not seen. All right. Now. Okay. Thank you. Look at this, students. What I written on the board is a Carnot engine. Understand that when you are talking about a Carnot engine, we are talking about a concept, and we are talking about a very ideal kind of engine which is having the maximum efficiency. Okay, so when I'm saying engine is having a maximum efficiency, please note that I'm not talking about, just a minute, just a minute. Okay, so let me draw a schematic of an engine. Okay, any engine. Any ordinary heat engine. What happens in any ordinary heat engine? It is supplied, and an ordinary heat engine rejects certain heat, okay, to the sink, means to the environment, and there is some energy which is being supplied by some source. Okay, so in ordinary heat engine, actually, this heat energy comes from the source, but this is the real source. This is the real source. Okay, and real source means what? For example, if you are talking about a petrol engine, the heat supply would come from combustion of petrol. Okay, if you are talking about a coal fired boiler, then it might come from combustion of coal. Okay, so heat supplied in the actual engines, the source is the real source where you are burning certain fuel, right? And in the actual engine, heat is rejected. You will find that in all the actual engines, the heat would be rejected to the environment. Okay, the heat would be rejected to the environment. So this is an actual engine. Now what does a Kelvin Planck statement say? Kelvin Planck statement says that the second law, Kelvin Planck statement says that all engines, all engines have to reject certain heat. Okay, so it means that the efficiency of this has to be always less than 100%. Always less than 100%. That you know, that you have understood, right? Now, what is a Carnot engine? Whether the Carnot engine is the engine where QR is equal to 0, whether the Carnot engine is the engine where QR is equal to 0. Can somebody answer this? Whether the Carnot engine is the engine where QR is equal to 0. Can somebody answer this? Ganesh? Ganesh is saying no. Zai is saying no. Anybody else? Yuraj is saying no. Roshan is saying no. Gauri is saying no. Very good. Pranoy is saying no. Very good. Right. Okay, so you are very clear on this now. That, let me close this now. Yes, most of you are saying no. So Carnot engine also rejects the heat. Carnot engine also rejects the heat. Please note. So Carnot engine is not the engine which is not rejecting the heat. So Carnot engine also rejects the heat, right? rejects the heat. So obviously, if a Carnot engine is rejecting the heat, if Carnot engine is rejecting the heat, its efficiency cannot be 100%. Its efficiency cannot be 100%. So Carnot engine also the efficiency is not 100%. Then how much is the efficiency of the Carnot engine? Then how much is the efficiency of the Carnot engine? So can somebody answer this now question? Carnot engine, the efficiency is not 100%. So how much is the efficiency of Carnot engine? What can you tell some value? Can you tell some value? Okay, Sai is saying maximum, Ganesh is saying maximum, Sharwar is saying maximum value. Can you put some number, some maximum, some number? Can you put some number to that? Abhijit is saying 70%. Yuvraj is saying less than 100. Maximum value, it could be anything. Omkar is saying that. Ritesh is saying 70%. Kunal is saying maximum possible value. Roshan is saying less than 100%. Neha is saying approximately 75%. Okay. So, okay, all right. So 70-75%, those who are saying they are wrong. Okay, you cannot tell. Okay, you cannot tell the value. What is the value of Carnot engine without specifying some other things? Okay, what are those other things? I will tell you later. Okay, but for the present purpose, you must just say that Carnot engine is the engine whose efficiency is maximum. It is not 100%. It is less than 100%. This we can say for sure. This we can say for sure. Then how much is the value of the efficiency? That can be calculated, but that would be done later. This has already been explained in the video. I will come back to the Carnot cycle. Okay, so what is the Carnot engine? So first thing is that it is an ideal engine. It cannot be constructed. It is an engine which rejects the heat. It is an engine which rejects the heat, and hence its efficiency is not 100%. However, it is an ideal engine whose efficiency is maximum. Now, what is that which makes this engine the best engine? Okay, I mean to say best ideal engine. Why is the engine having the maximum efficiency, and why the other engines are not having the maximum efficiency? Okay, that you need to appreciate. Okay, for appreciating this, that why this engine is having the maximum efficiency and why not the other engines have the maximum efficiency, you need to understand the Carnot cycle. Okay, so in order to discuss the Carnot cycle, I have first, okay, or I will discuss it and then I will raise the questions, because it appears that many of you haven't seen the video. Okay. So this Carnot engine is the engine which Carnot engine is the engine. Okay. Carnot engine is the engine which executes the Carnot cycle. Now, what is Carnot cycle? Carnot cycle is a set of 4 processes. It is a thermodynamic cycle. So you know that any thermodynamic cycle is basically a set of processes in a particular order which gets back to the initial state. What is a thermodynamic cycle? It is basically a set of processes in a definite order which will get you back to the initial state. So wherever you start with, you have to come back to the initial state so that the cycle is completed. Okay, so the Carnot cycle is a thermodynamic cycle which has got 4 thermodynamic processes. Okay, so the 4 processes you can start from anywhere. Okay, because it's a cycle, so you can start from anywhere, but I would like to start from the heat addition process. So this is a Carnot cycle has got certain heat addition. There is heat addition happening in the Carnot cycle. That is, in the Carnot engine there would be heat addition. Okay, and this heat addition in the Carnot cycle is a reversible heat transfer. Okay, we have discussed this in the last lecture. I had discussed this in the videos also. We have been discussing this, that what is the concept of reversible heat transfer. So in the Carnot cycle, the heat transfer is reversible, and this reversible heat transfer happens from the source to the working fluid, right? isothermally. Okay, so how do we imagine this? We imagine that this engine receives the heat from a source. Okay, it is now the ideal source I am talking about, not the real source. And this engine receives the heat from the source. This is the engine, let us say Carnot engine, and this heat transfer is reversible. Meaning what? Meaning is like this. Let me discuss this. This heat transfer is reversible. So let us assume that the source is at certain temperature TH. Now we have already discussed the concept of source. Source is an imaginary reservoir which can give any amount of heat to the working fluid of the engine without the drop in its temperature. So the source temperature is not going to change. It will always remain TH. Okay. And the working fluid of the Carnot engine would accept this heat, okay, reversibly. Meaning what? The meaning is the working fluid, okay, the working fluid of the Carnot engine would accept the heat, at certain temperature. And what is that temperature? That temperature is almost TH. It is not TH. It is almost TH. Please note. It is almost TH. So the temperature at which the working fluid of the Carnot cycle or Carnot engine accepts the heat from the source is at almost TH. Okay. Why I'm using the term almost TH? Because you know that for the heat transfer to happen, there has to be certain delta T. Okay, without which there cannot be a heat transfer. So now we are all talking about very hypothetical kind of engine. So in this hypothetical kind of engine, if this heat transfer has to be reversible, then this delta T, that is TH minus this almost TH, has to be negligible, has to be infinitesimally small. Okay, it has to be negligible. Are you getting this point? So Carnot cycle, one process is of heat addition, and this heat addition is a reversible heat addition from the source to the fluid, and now this happens isothermally. Now how can we visualize this by some method? Okay, so let me draw some kind of hypothetical engine, okay, to show you this process 1 to 2. Okay, so one of the process in the Carnot engine is what? Let me erase this first. I'm not able to. Okay, I will erase this. So in order, okay, as I said that in the Carnot engine, one of the processes is the isothermal heat transfer. Now in order to visualize this, okay, this kind of how can this happen? Okay, so we would consider that imaginary. Okay, this cannot be constructed. Please note, but we can just think of this kind of stuff. Okay, some imaginary piston cylinder arrangement which is frictionless, which is frictionless, which is insulated, can be constructed. Okay, you know that in actual practice we cannot have a frictionless kind of piston cylinder arrangement. That is why I'm saying that we are talking about imaginary engine. Okay, frictionless. Okay, and this is some fluid. And there is some lead to this engine, which can be removed and which can be added to the engine. Okay, this is the removable detachable lid. Okay, detachable lid which can be added or removed. Okay, and how is the process happening? How is the process of heat transfer happening in this hypothetical Carnot engine? So what we do is that we bring this source, we remove this lid and we bring the source in contact with this fluid. Okay, so what would happen is when you are removing this lid and bringing this source in contact with the fluid. Now what would be the temperature of the source? The temperature of the source would be TH, right? And what should be the temperature of the fluid? This temperature should be almost TH. Okay, I am just putting some word dash. Okay, and please note that this TH and TH dash are almost same. Okay, so TH dash and this TH dash is almost equal to TH. Okay, So for practical, for conceptual reason, we would say that the fluid accepts the heat at the source temperature. This fluid, working fluid, would accept the heat at the source temperature, and this heat transfer has to be quasi-static. It is a reversible heat transfer. Reversible heat transfer. Why is this heat transfer reversible? Because this temperature difference is negligible. Temperature difference is negligible, right? And then when you are having this, when this fluid is accepting certain heat, okay. Now, if you apply the first law of thermodynamics to the process 1 to 2, what is the process 1 to 2? Process 1 to 2 is the heat transfer process. Okay. In a Carnot engine, what is the process 1 to 2? It is a isothermal. It has to be isothermal, means constant temperature. It is a reversible. It is not only isothermal, but it is also reversible heat transfer. Heat transfer. Okay. This is the first process in the Carnot cycle. Now, if this has to happen, then what has to, if you apply the first law to the process 1 to 2, you know that Q is equal to delta E plus W. Okay. 1 to 2. 1 to 2. Because the temperature has to remain constant, this has to be 0. This has to be 0. It means that this piston, okay, the frictionless imaginary piston, would start moving away from the lid. It means that this is an expansion process. This is an expansion process. Okay, expansion process. So what is the process 1 to 2? Process 1 to 2 is the reversible isothermal heat transfer accompanied with expansion, expansion work. Okay, so the temperature would remain always constant when the heat is being added. And what would be that temperature, constant temperature? That constant temperature would be almost TH. It would be almost TH. Now, what is the next process? The next process is an expansion process. It is an expansion process. Okay, but there is no heat transfer. The next process is an expansion process, and there is no heat transfer. In the Carnot engine, if this has to happen, and if there has to be no heat transfer, then what we need to, if this has to now become 0, this has to be stopped. The heat transfer has to now stop. Okay, so we need to stop this. So how do we stop this? You can place a lid, okay, which was detachable, and this is also insulated. So place a lid on this. So when you place the lid on this, what would happen? What would happen is the heat transfer would cease. The heat transfer would stop. Okay, so let me represent this process on a pressure volume diagram. So we are talking about expansion, and you know that expansion means there is a drop in pressure, increase in volume. Drop in pressure, this is 1 to 2, and then there is a 2 to 3. Okay, so this process is basically both this 1 to 2 and 2 to 3. They are expansion processes. And what is the difference between process 2 to 3 and process 1 to 2? In both the processes, expansion is happening, but in this process, the heat transfer is 0. So this, if you apply the first law of thermodynamics here, then this is 0. It means that this expansion can happen. But only if this decreases. Okay, this you can put some numbers and convince yourself that this expansion can happen only if the temperature drops. So what happens is the process is, this is a no heat transfer. It means that the process is adiabatic. Okay, there is no heat transfer with the surroundings, so process is adiabatic expansion, and there is a drop in the temperature. And you are getting certain work output. You are getting a work of expansion 2 to 3. Okay, so these are the two processes on the Carnot cycle. So 1 to 2 is isothermal reversible heat transfer. 2 to 3 is adiabatic expansion. Okay, where there is no heat transfer because you are putting the lid on it. Okay. Now, what is the next process? So the next process is that we need to just reverse now, just go on repeating these processes now. So 1 to 2 is isothermal reversible heat transfer. So 3 to 4 would also be isothermal reversible heat transfer. Now, how to visualize this? How to visualize this? Okay. So for me to visualize the process 3 to 4, okay, 3 to 4, what I will do is that, okay, let me rub this diagram first. I have already shown you 1 to 2 process, which is how is that executed? 1 to 2 process is executed by bringing the source in contact with the working fluid of the Carnot engine, hypothetical Carnot engine. Okay, 2 to 3, how it is executed? By putting this lid and making sure that the heat transfer no longer takes place from the source. Now 3 to 4, for 3 to 4 to happen, what I need to do is that, and now before the beginning of the process 3 to 4, the piston is, the piston has already reached the dead center, the bottom of this. Okay, so now let us say this is the final position. Now piston cannot move away, right? It has reached the dead center. Now the next process would be, now in process 1 to 2, the piston was moving to this side away from this lid. Process 2 to 3, the piston was going to this side. It means that both during process 1 to 2 and 2 to 3, you are having expansion. The difference between 1 to 2 and 2 to 3 is that 1 to 2 is isothermal heat addition and 2 to 3 is that there is no heat addition. Okay. Now the third process 3 to 4 is again a heat transfer process. Again a heat transfer process, and again that process is isothermal. That process is isothermal and reversible. That process is isothermal and reversible. Now how do we have this process? How do we execute this process? So for that we need to imagine that this engine is brought in contact with the sink. We need to imagine that this engine is brought in contact with the sink, and what we do is that again we remove this lid. This lid is again removed. So what would happen? Just imagine, this is a fluid, and now it has reached the lower temperature. What is the temperature it has reached? It has reached TL. This fluid, when it has reached, what was the temperature during process 1 to 2? The process 1 to 2, the temperature was TH, almost TH. Okay, when I'm saying TH, so at 1 also it was almost TH, and at 2 also it was almost TH, right? So the temperature was constant. Now 2 to 3, what happened? At 2 it was TH, and then at 3 it became TL. At 3 it became TL. So there is a reduction in temperature from TH to TL. So it's almost TL. Okay, it's almost TL. So now the working fluid is at almost TL temperature. Almost TL now means what? It is slightly higher than the sink temperature. Now at this position, this working fluid is at a temperature TL. Okay, which is almost TL, I'm saying, which is at a higher temperature than the sink temperature, but it is that temperature difference. That temperature difference is negligibly small. So if that happens, if that temperature is negligibly small, then there would be a quasi-static heat transfer, a reversible heat transfer. It is quasi-static, it is reversible heat transfer from this fluid, from whatever fluid you take, from this fluid to this sink, and that is a heat rejection. Heat rejection. And how is this heat rejection during the process 2, 3 to 4? That heat rejection is a reversible heat rejection. It is a reversible heat transfer. And why is that heat transfer reversible? It is reversible because the temperature difference is negligibly small. The temperature difference, that is almost TL and TL temperature, difference is negligibly small. Please note, that is why it is reversible. And why is it isothermal? It is isothermal because now you know that if there is a heat rejection, the internal energy will decrease. Okay, if there is a heat rejection, the internal energy should decrease, right? But because we are compressing it now, we are moving this piston towards this lid, towards the top dead center. We are compressing this piston now. Okay, we are compressing it in such a manner. That whatever is the decrease, okay, again if I apply the first law of thermodynamics to this, Q3 to 4 is equal to delta E plus W, 3 to 4. Okay, W3 to 4. So if this delta E has to be constant, means if this has to be a isothermal process, if this has to be an isothermal process, if this delta E has to be 0, sorry, delta E has to be 0, then whatever is the heat rejected, which would try to decrease this, internal energy, has to be compensated, by supplying certain work. So you need to supply certain work 3 to 4. Okay, so there is a work input during the process 3 to 4. Okay, so please note that the process 3 to 4 now is a isothermal reversible heat transfer accompanied with compression. Isothermal reversible heat transfer accompanied with compression. And then what is 4 to 1 process? 4 to 1 process, how do we execute? Again, if you remember our first discussion, what we do is that in the process 4 to 1, there has to be no heat transfer. In the process 4 to 1, there has to be no heat transfer, meaning that the process 4 to 1 is an adiabatic process. And how will that be adiabatic? That will be adiabatic only if we bring this lid back to this piston cylinder arrangement. So if we bring this lid back to this piston cylinder arrangement, this heat transfer would cease. Heat transfer would stop. Okay, so the heat transfer would stop, right? The heat transfer would stop, and the piston would continue compressing. The piston would continue compressing the fluid. Okay, so the piston would continue compressing the fluid, as a result of which, its temperature would get back to TH. So it was TL initially, it will get back to TH. Are you getting the point? So please note that in this Carnot engine, there are 4 processes. There are 2 processes which are reversible heat transfer phenomena. There are 2 processes which are reversible heat transfer phenomena, and there are 2 other processes where there is no heat transfer. Okay, so with my nomenclature, with the nomenclature which I used, I would say that in the process 1 to 2, and in the process 3 to 4, in the process 1 to 2 and in the process 3 to 4, there is a reversible heat transfer, and that leads to an isothermal process. It is an isothermal reversible heat transfer. So there are 2 isothermals in the Carnot engine. One is the isothermal reversible heat addition, other is the isothermal reversible heat rejection. Reversible heat rejection. So there is one heat addition, one heat rejection in the Carnot cycle. Okay, and how is that heat addition taking place? Heat addition is taking place reversibly, and heat addition is taking place isothermally. How is the heat rejection taking place? Heat rejection is taking place isothermally, and heat rejection is taking place reversibly and isothermally. Okay, it is taking place isothermally and reversibly. Now, what are the other 2 processes? The other 2 processes are simply the processes without any heat transfer. Other 2 processes are without any heat transfer. They are adiabatic processes. One of that process is an expansion process, and other process is an compression process. One of the process is an expansion process in which the temperature drops from TH to TL, and the other process is a compression process in which the temperature again gets back to TH, almost TH. Okay, when I'm saying TH, I am saying almost TH. When I'm saying TL, I am saying almost TL. Okay, so this has to be, I guess this is clear to you. If this is clear to you, I hope you would be in the position to answer my questions now. Okay, so let me take the polls. From the result, whatever you are answering, it appears that 60% of the class is attentive. Others, 65% of the class is attentive. Others are, I hope they are just relaxing. Okay. It's a very straightforward question. This was repeated again and again. This point was repeated again and again. And this was also explained in the video. So looking at the responses, it appears that there is still confusion. So let me close the poll. See the result. I hope the results are seen to you. A very straightforward question it was, wherein I was talking about a heat addition process. So if there is a heat addition process, it cannot be adiabatic. Adiabatic means what? Adiabatic means there is no heat addition. Okay, there has to be no heat transfer. When the process is adiabatic, the heat transfer has to be zero. So obviously, those who are answering it that it is an adiabatic process, they don't understand what is the meaning of adiabatic process. The meaning of adiabatic process is that there has to be no heat exchange. There has to be no heat exchange. So if there is no heat exchange, there is no question of heat addition. So obviously, first cannot be the answer. The 60% of the students who are understood, they have correctly expressed it as a reversible isothermal process. Okay, so the correct answer is it is a reversible isothermal process. Some of you, very small number, they are calling it as irreversible. There is no question of irreversible process in a Carnot cycle because Carnot cycle is a reversible cycle. Okay, so I'm hiding this and I'm going to the next question. You need to be fast in voting. I will be capturing your attendance in the polls. In fact, the first poll is very important where I will be seeing your attendance there. So this is all, I guess, your responses. 50% of the class, or not 50%, around 40% of the class is responding without listening to the lecture or to the videos. Okay, this is very obvious to us. We would find out those students. Okay, if you have any special reason for not listening to the videos or not listening to the lectures and answering the questions, we would be glad to know these reasons. Okay, so you can send your reasons via WhatsApp, that why you are not listening to the lectures and why you are not listening to the videos. Okay, so there's 30% of the students who are answering incorrectly, 30 to 40%. Make sure that all these concepts in thermodynamics, what is more important for you to understand is, this being a demanding subject, you need to go to the concepts again and again. It is not that you listen once and you would understand it. You'll have to revisit the concepts again and again so that you appreciate them better. Okay, and this is a very important cycle without which you won't be appreciating the other thermodynamic cycles in thermodynamics. You won't be able to understand what exactly the Carnot theorem is without knowing what is a Carnot engine. Next question. So 50% of the class have understood the concepts. I hope that is not very satisfactory from our side. So I would be closing this polls, and I'm also closing this webinar. The advice is, students, dear students, that you need to get back to the videos which were shared with you, and you need to listen to them again and again till you understand this Carnot engine perfectly. Okay, that is the only thing I can advise you now. Okay, thanks for joining. Bye.